So I'm going to talk about particle physics or the smallest bits of the universe that do matter. So I will talk about building blocks, particle physics, elementary particles, atoms, and so on. So what I'm working on is the fundamental blocks of matter, and we try to study them by looking deeply into ordinary matter to see what ordinary matter is made of. So I start, if you want, from the end. So this is a graphical representation of my job. What we have here is a computer representation of an event. We call this an event display because it is displaying the collision of two particles. You have to imagine that you have protons coming this way and the opposite way, and they collide in the point where you see this spray of colored objects. So we use particles, we make them collide, and we study the result of the collisions. Protons, as it was already said, are everywhere here in the rest of the universe. They are in nucleus of atoms, and we are all made of atoms. Stars are made of atoms. Everything that we can see is made of atoms. The reason why we call it dark matter is that it doesn't emit light, but I'm going to talk only about ordinary stuff, or at least what we discovered so far. So the ingredients of my research and this talk are particles, a collider, because we need to accelerate them, to energize them to make collide, and then a detector, that is this thing that is a bit exploded and open to detect the result of the collisions, because we are going to produce way more particles than the one that we put in the collider, but I will explain this in a moment. So, but few questions first that you might have. Why do people get interested into this? Why do people want to see what is inside matter? Second, how do you do it? And third, and who are you? So the first part was a bit introduced by Sonia. So I was born in Italy. I grew up in an incredibly tiny town compared to Paris that is called Pordenone. It is northeast of Italy, but it matters to me. So you see, it's also a nice place. And then I moved to Trieste, that is in the same region, a bit more south and east. And it's a city full of science. There is plenty of research institutes, not only for physics, but for biology, geoscience, and so on. And to my opinion, is also full of beauty. It is facing the sea, but it is mountain very close. So if you have the opportunity, I suggest to visit. And then I moved to Paris. You recognize this building, you can see it over there. And the other is a bit hidden, but basically I am just around the corner if you pass by and you want to say hello. Okay, that cleared out. The question is, why do people get interested into this? Well, it's true that Gabriel spoke of the large scale, but you can also address the question of what we are made of by looking down at the smaller scales. Because again, everything that you see in this picture, everything that is bright, is made of something that we know quite a lot about, that is ordinary matter. And to answer, so the primordial question is, what is matter made of? And the other is, why it is organized in this way and not another one? And so this is, these are the questions that we are still today trying to answer, but we have a good description of some of the effects that we see. But you remember that I say why people get interested into this. I can tell you, for example, who started to get interested into this, and that he had quite good ideas. And it was 25 centuries ago. It was Democritus, one of the atomists, and he was a philosopher. And he came up with the idea that everything is composed of atoms, and which are physically indivisible. Because atoma, apologies for my bad Greek pronunciation, means indivisible. So the idea he had is that if I cut something down, 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 at a certain point I have to stop. There is my grain of fundamental stuff. That was just pure thinking, no experiment, nothing to support that. And between atoms, there lies empty space. And atoms are indestructible. This is another important point. If at some point you cut down so strong, you cannot go beyond that. Something starts to be stable and indestructible. And have always been and always be in motion. This is something that astonished me when I read it the first time, because okay, one could imagine that either there is continuum or discrete stuff. Either I stop or not. But having also in mind that they move constantly is something that it took 25 centuries to be proven. So size is what matters in this talk, because we really want to see, I stress that again, what is at the smallest possible scale. So we have biological beings at the scale of meters or several meters, and then we go down, we start to see what is inside living objects. We have cells, and then inside cells we start to see that there are proteins, and proteins are made of molecules, and molecules are made of atoms. You see here that the more deep we go, the tool we are obliged to change the tool, and this is linked to an idea of the scale of the object. We need to change the wavelength that we are using to look into. You use X-rays, you use gamma rays, then you move to electronic microscope. What is beyond atom? Because we didn't stop. We have inside the atom, we discovered there is a nucleus with a cloud of electrons going around, and you see that when we move from the atom to the size of the nucleus, there is a factor 10 to the 1,000 in size. So the nucleus is something very small compared to the size of the atom, and then we look at inside the atom, and we discovered that the nucleus, and it is made of even smaller grains, and we have the protons and the neutrons. But that's not the end of the story, because we go down another factor 1,000, and we arrive to discover that inside protons there are quarks. So we moved like almost 1 billion in size from the atom to the quark. It turns out that also the electron that is revolving around has up to date this size, but it is an upper limit. So we tested up to this size. Maybe it's smaller, we don't know. But at the moment, if you want, quarks and electrons are what Democritus was calling atoms. They are fundamental. We don't see any substructure. We are trying to cut them more, but we are failing. They still remain as a point. But our meters have this sensibility. So to give a comparison, because it is easy to get lost with these numbers, I also get lost. Remember that a hair has a diameter of 10 to the minus meters. So it is 10 micrometers, if you are familiar with micrometers, or is 100 of a millimeter. If we look at the size of an atom, we see that inside a section of hair diameter, we expect to have 100,000 atoms. And then you have to go down to this small number. But the interesting thing is that if we compare the diameter of an atom with the diameter of a proton, we discover one interesting thing, that if protons would have a diameter of 10 centimeters, then the atoms would be 10 kilometers in diameter. So there is a lot of empty space. Actually, an atom is 99.99% made of vacuum. Look who's right. Democritus got it right. Between atoms, there is empty space. Inside each of us, it is plenty of empty space. So the image of an atom like that on top, it is nice, but it's wrong. It's something super condensed, almost all the matter is in the nuclei, and then you have the electrons, let's say, revolving around. Then quantum mechanics says there is no trajectory, nothing. It is a cloud, as I said, but you can imagine that they are orbiting a bit like the Earth is orbiting around the Sun and all the other planets. So this is down here, the smallest scale that we investigated so far. We try to go further, but it's difficult. We will see why. So, but which are the particles that we can consider atoms? So historically, at some point, we had the periodic table of elements, and we were pretty satisfied. We could explain all the kind of materials that we had around. But typically, when scientists see that the number of fundamental elements is so big, more than 100, they suspect that there is something fishy going on. They suspect that there is a substructure, and so they start going deeper. So if you have something that you retain that is fundamental, but it is in number of hundreds, typically you say, no, these are composite objects, and this is what happened because we discovered, as I said, the nuclei, the electron, and so on. And plus, citing a Nobel Prize in physics, if I could remember the names of these particles, I would be a botanist without any offense for botanists. So what is the actual picture of standard matter that we do understand? We have a standard model also here. Gabriel mentioned the standard model of cosmology, and this is the standard model of elementary particles. They are not 100, they are a few, and you see that we can count them, is 6 plus 6 makes 12, 16, 17. I don't put here antiparticles, but you can imagine that for each particle you have a twin that is called the antiparticle, as it was said. But ultimately, what is matter made of? If you want really to cut it down, the ordinary matter we are all made of, the stars and so on, is just these three objects. Inside the proton and neutrons, you have quarks up and down. At certain point, we didn't have any more fancy name, and we started to name, okay, you are up, you are down, and that's it. We ran out of fantasy, because remember that we compiled all this, so we were already exhausted, and we say, we hope that you are the last, so we give you simple names. Then you have, the electron. And you remember that I said we want to know which are the fundamental blocks and how do we connect them. And in a theory that it is at the basis of this standard model, the interactions are mediated by another kind of particles. And this particle on the left exchange the particle on the right to interact. A common way to picture this is, suppose that you are standing on a boat and you have in front another friend that is standing on another boat, and you start exchanging a ball. You know that you will, little by little, move backward. Because each time that you receive a ball, you receive what is called impulse, so the product of mass times velocity. So that's how we model this. So everything, if we want, can be summarized into particles. Also, these objects cannot be cut into half. So the photon is responsible for all electromagnetic effects. The gluon is the one that is gluing together the up and down quark in protons and neutrons. You have the W and the Z that are responsible for radioactive decays. And the famous or infamous Higgs boson is the one that is giving mass to all these particles. So all you need to know, and all that is known today for particle physics, is here. The question, of course, is what are all the other objects? Well, it turns out that typically if you find a fundamental particle, it has an heavier sibling. So muon, for example, is in all aspects the same thing as the electron, just its mass, whatever, it doesn't matter the units here, you see is 200 times heavier. When muon was discovered, a Nobel Prize said, who ordered that? We don't know, but it exists. And then you have another heavier object that is called the tau, and so on. Then you have the neutrinos that are a bit peculiar because they don't have charge, they have very little interaction. And then also for the quarks, you see down has two heavier siblings and also up has two heavier siblings. Note also that there with the names we were in crisis. We call it strange because we didn't expect that. So what is this strange particle? It's true. And then since we found strange, we said, well, what is the opposite of strange? Maybe charm. And then it was charm. And then, of course, up and down you took, and then you say, okay, let's go for bottom. And then, of course, opposite to bottom, there is top. At the moment, we don't have a theory that says there will be no heavier replicas. But typically, the theory says, if you want a heavier replica, don't put just one. You have to repeat this pattern, not only for the particles that are like the quarks, but also for the particles that are like the electron. But how we managed to arrive to this picture? So particle physics, again, is about the building blocks of the universe. And Lego is blocks and rule how to connect them. And in the end, as I have shown you, particle physics is the same. On the left, we had building blocks. On the right, how to connect them. So this analogy is not coming from me. There are excellent colleagues that use this several times. And okay, but the question now was, how do you study these building blocks? Well, what you do, you take an object, a particle that you know very well, an electron, a proton, something that is possibly stable. I didn't mention that most of the particles that were there are unstable. They decay to lighter objects. In the end, the stable particles are the proton and the electron, maybe the neutrinos, but maybe not. And so you take this proton and you shoot it against either a target made of matter or a single particle. And what happens is that you accelerate it, bang, and you look at what comes out. Remember the first picture that I show? You have the protons colliding, and then you see the spray of particles. So this is what we do. There was a Nobel Prize that says it's like if to discover what is inside the vase of flowers that your grandma has in the living room, you crush it on the ground to check what is inside. Grandma can get mad, but you learn something. So how do we do it, really? So CERN is the European laboratory for particle physics, and at CERN it is hosted the largest particle collider ever built, that is called Large Hadron Collider. So it is called hadron because protons, for some reasons, are called hadrons, and indeed we collide the protons there. So how does it work? You start injecting protons into a first ring to pre-accelerate them, and then you inject them in the huge ring that you see here, and they will make several turns to arrive to the highest possible energy of this collider, that is the most energetic one, and then they enter in collision, producing pictures as I have shown, in one of these 4 points that you see. Some numbers. Okay, it is sitting at the border of France and Switzerland, close to Geneva. It is 100 meters underground, and the circumference of the collider is 27 kilometers. We accelerate the protons thanks to electric fields and magnetic fields. Magnetic fields are used to bend the particle, while the electric field is giving them a kick to go faster. At certain point, these protons are so close to the speed of light that it is more interesting to check which is the energy of these protons rather than their speed. Because when you see that is 99.999999999% of speed of light, yes, but so what? So what you do, you compare their energy to their mass, because thanks to the equation of Einstein, we know that mass is one form of energy, and the equation is energy equal the mass times the speed of light. So here they go at, they acquire such an energy that the beam itself, which is made of 100 billion of protons, which is very little as mass. We have, you know, in 1 gram of matter, we have the order of one number of Avogadro of protons. Number of Avogadro is 10 to the 23, so is 100,000 billion. Here there are just 100 billion of these protons, and still they are so energetic that they have the same energy of a TGV at 120 kilometers per hour. So this thing has to be so big because they have to make many turns, and when they get so energetic, if the radius was smaller, the magnets needed to bend them would be too powerful and we cannot construct them. There is a new project, but the limitation is that. So if you want to go up in energy, you have to do 3 things. Put more powerful electric field to a technique that is called radio frequency, so you have an oscillating magnetic electric field. You need stronger magnets and larger radius. So, okay, we understood how you energize this particle to shoot them one head on the other. Then we have this picture, but how did you get this picture? How do we see particles? Because remember, the size is something so small that there is no possibility with standard microscopy to see them. So what we do to see them, we use an atlas. a gigantic experiment. So you have, you remember in the image before, there are collision points. This one is the one where Atlas is installed. So protons arrive from two sides, collide in the center, and then we see, thanks to this detector of particles that is made of several different layers, we see the result of the collision. So some numbers about Atlas. So it in height is 25 meters, in length is 44, so it's like a nice cathedral, and the mass is like the Eiffel Tower, so it's huge. It's very difficult to get a picture of Atlas because it fits exactly the cavern, and so there is no good point to take picture. It didn't put any picture, but if you go online and you look for CERN Atlas, you can see some slices of it, so still the graphical representation, I think it is the best. Note that the people have the correct scale. And it is a giant camera that takes 40 million pictures per second, because one thing that I didn't mention, we collide protons every 25 nanoseconds, which means that every second we have 40 million pictures. So this thing is capable to take the image that I have shown at the beginning, 40 million per second. Most of the stuff, we know it already, so we dump it, because we look for rare events, for what we don't know. I will come to this in a second. So at the core of this object, you see that I put a small circle there. There is what is called a tracking detector. That is a detector that is used to measure the trajectory of charged particles, because this thing is immersed in a magnetic field that is oriented as the axis of the beam. So the particles that go out don't go straight, but if they are charged, they make circles. If they make circles, we can measure their speed. So at the core of this object is written here. So now we go again to small scales. There is something that is called a pixel detector. That is the detector on which I work on. So this is my job. Nowadays, we have a certain number of collisions that are produced for every crossing of bunches of protons. But if we want to know more, we have to produce more collisions per turn. So the image that we had before, it will become that one in 2027. So everything will be more crowded, more dense. There will be up to 4 times, from 4 to 10 more interactions every 25 nanoseconds. And we need to separate all this situation. Nowadays, we use silicon detectors that are segmented in 2 ways. You see, this is more or less the size of a human hair. This is a very thick human hair. And each of these cells that you see is read out independently. So if one of these elements says, I have seen something, we know that it passed more or less here with this precision. But if we have to disentangle all that situation there, we need to make smaller pixels. So the plan is to go, instead of 50 times 250, to gain a factor 5 and go 50 times 50. Because smaller pixels means better precision. By the way, in all the cameras that you have here, or in your digital reflex camera that you have at home, you have this kind of technology. Actually, pixel means picture cell. And what you have in your devices, in your mobile, it is a piece of silicon that is segmented a bit like this, and your detector there is able to say, I have seen a red photon, I have seen a blue photon. Each one is answering, and then you get your sunset picture. What I do here, on the contrary, I want to know if a certain signal was seen by the pixel, which correspond to the fact that a particle traversed it. So what I do numerical simulation of the new detectors, I realize them, I build them, I measure them on beam, I publish results and so on, but I wanted to show you this picture. So the Atlas collaboration that is running the detector and analyzing the data is made by more than 4,000 people. I don't know all of them, but in my small group, I had the chances to meet a lot of very nice people from all around the world. So it's an incredible experience from the human point of view. It is really, really beautiful. So, but what do we see? So I want to show you one way in which we can discover something new. So we go back to a picture that is similar to the first one. It is slightly different. But now we know that if we see this, we had 2 protons coming this way. We have this spray of particles. We see other details of our detector. And we focus our attention to these 4 red lines. These 4 red lines are a measurement of muons that passed. Muons is the heavy brother of the electron, the one that the physicist said, who ordered that? We don't know, but we deal with that, there's no problem. So what we do, we look, for example, for events, remember, 40 million per second, and we collect data for years to have enough statistics, and we consider these 4 objects, and we sum the energy of this object, and we put this sum of energy into a graph. So, quickly, in red you have a process that you know. Also in purple you have a process that you know, and you want to check if somewhere there is an excess with respect to what you know. And data is telling that here there is something that you don't know. So you see that everywhere the data are superimposed to the colored histogram, apart here. Here there is an excess. Here is the way in which you find, for example, the Higgs boson. Then you know I have a theory, and I want to see if my theory agrees with the data that I have seen, and you superimpose the new effect. And thank you for your attention.